have no charge because the theoretical charges were all 0. So now let's move on to the next question. Which statement best describes O3? Okay, so that would be your oxygen. Okay, and they're wondering which statement best describes it. Okay, and that's very strange because they have, well, I guess that's a separate question after, but each atom in ozone is connected to an atom by a bond having a bond order of 1.5. Wow. The double bond in ozone switches back and forth between the two outer oxygen atoms. An ozone molecule contains one single bond and one double bond. Okay, so with this being said, the way to tackle this question is to first understand what ozone is by drawing this Lewis dot diagram. Okay, so oxygen, all right, is the eighth element. Okay, so using both just the column it's in and the electron configuration, which is something I like to do in the shorthand notation, we can actually see that oxygen has 6 valence electrons, being the 8th element. Specifically on the things on the 16th column typically have 6 valence electrons, and also can be supported by the electron configuration. But there's 3 of them, so we need to account for 18 electrons. Okay, so with that being said, we have one oxygen in the center at least, sharing one bond on each side with another oxygen. And because oxygen comes with 6, okay, this oxygen on the right and the left need to fill at least that part up. So it's going to have 2, 3, 4, 5, 6, okay, and then the other oxygen, same thing, 2, 3, 4, 5, 6, all right, and then the oxygen in the middle is sharing right now 2 of its 6, so 3, 4, 5, 6. So the oxygen in the middle is actually completely satisfied, but this setup doesn't work because the oxygen on the outside have these radical lonely electrons. So what's actually going to happen here is that no, these two do not bond with each other from across. You don't end up with like a triangle for ozone. That is actually not how it's going to work, unfortunately. I've thought about that, and no, it's not the case, unfortunately. So what actually happens here is that this is going to split and form a double bond with one side of the oxygen. This is all theoretical, by the way. You'll see later it's not actually a double bond, but this is what happens on this side, and on this side, this oxygen just takes it. Because the reason why it cannot be another double bond is because then the oxygen here in the middle would break its octet rule. It would have 2 double bonds on each side, and also it would have a lone pair. So that's 5 things in total it'd be quote unquote attached to. And that's not, well, not 5 things. It would be 10 instead of 8 electrons that it would have surrounding it, which is not what it wants. So with that being said, if we redrew this, okay, we'd have O, okay, and this is what we get. Okay, so it still fills its octet rule for the central oxygen, and each oxygen on the side has filled its octet rule as well. And the theoretical charge for each oxygen, okay, would be starting from the right, and we're going to go to the left from there. So it's going to be 6 because that's its valence electrons, minus it has 4 electrons by itself, and it's sharing 4. So you divide that by 2, so 4 plus 2, that's equals 0. The oxygen in the center, okay, it actually only has 2, and it's sharing 6, so it's actually going to have a charge of +1. So this oxygen here has a charge of +1, which makes sense because the oxygen all the way to the left, okay, that one there, it's going to be 6. It has 6 already by itself, and it's sharing only 2 of them. It's going to be -1 because 6 plus 1 is 7, and 6 minus 7 is negative 1. Okay. So now, with all this being said though, we could have just answered the question saying that, oh, well, that means that ozone contains one single bond, one double bond. That would be technically incorrect, because now you have to factor in your resonance, okay? Another resonance structure for this, which I could have equally drawn as well, which is not the same thing, would be this. You may have said that, wait, you just flipped it over, but remember that these are all separate separate atoms with their own identities. What I've done is that I've said that this oxygen on the left receives the double bond instead, and this oxygen on the right has now the negative charge, and this one would actually be -1 here, still positive in the center. But now we have two different types of resonance structures. So what you see here is that typically what's going to happen to get the maximum stability is that the electrons actually will be shared, to where instead of you having a single and a double bond, you would actually technically have it would kind of look like that, okay, to where one of the bonds is like dashed out, because it's not that the single double bond or like the double bond is switching back and forth. You actually have a complete structure where you kind of have 1.5 bonds, theoretically, okay? In this case, it would be like a pi bond and a sigma, or is it sigma pi? I think it's sigma first, then pi after. Kind of like that. This is what you'll be dealing with, where they're sharing that pi bond-ish to where it forms that resonance structure. Point being is that here, each oxygen has more so of a 1.5 bond, okay? Not that it's 2 and 1 and it's bouncing between, is that the whole structure, the electrons are moving through the whole thing, kind of creating that 1.5 bonds on each side. So with that all being said, the most correct statement is here. Each atom in ozone is connected to the other atom by a bond having the bond order 1.5. This is the most correct statement. That's why the answer for this one is A, the first choice. Because a double bond, as I stated, is not switching back and forth. That's just when you represent the resonance structure. But you want to be able to get the whole picture of resonance, because the resonance structures are just simply, I guess, possible extremes of when the electrons are moving about. But you know, you don't want to go for the extremes. You want to go for what's most probably going to happen, which is that the electrons are somewhere in between the two oxygens at the end. And because they're somewhere in between, we say that's around a 1.5 bond on each side. There could be a moment in time where it's like 1.7 on one side and 1.3 on the other, or really close to 2 on one side and really close to 1 on the other. But point being, on average, it's going to be about 1.5. And the last one, ozone molecule contains one single bond and one double bond. As you've seen here as well, that is not the case, okay? It's neither just a single and double bond, it's more like 1.5 bonds. So with that being said, the correct answer is the first one. It does not contain a single and double bond. It's kind of just a mixture, okay? It's more so 1.5 bond. So this is correct, okay? So let's move on now to question number 7.